Hello everyone, I'm Sherry Sahibi and this is the data mining class. We are going to talk about artificial neural networks today. So what are neural networks? They are some way to some of the machine learning models that they were very popular at the rise of AI in 1980s, and then they went down, and again they are very popular after 2000. Maybe 8, 10. So neural networks are based on what we thought that the brain is going to work with. So they are basically are following a similar structure to the neurons and synapses and all of those in the brain. So what they have is that they are consisted of some cells. Let's say they are neurons. So for example, suppose that this is our neuron, and let's call it Z, and it does have some inputs, and then it does some functions on the inputs, and eventually it is going to have some outputs. So the inputs, let's call them XIs. Usually they are connected with a neuron with a weight, let's say WI, and then they are having some outputs, let's say YK. So this is this neuron is a basic unit for a neural network. This neuron can be connected to other neurons, or it can be connected to our input data or output data layer. So for example, on this side, you can have other neurons, or you can have the input layer that is connected to your data, basically. So if you want to talk a little bit in more details, this neuron is usually divided into two parts. One part that calculates a dot product, usually between the input and the weights that are coming in, and then another part that applies a usually nonlinear function on that dot product and then produces the output. So for example, suppose that we have a very simple structure, and we have our input data. So input data, one record at a time. So we have, these are our D features in our input data. It is augmented. So for example, we have x0 here, x1, x2 until xd. These are our input nodes, and they are all connected to a neuron. This is the simplest case that we can have for a neural network, and they are all having weights, different weights. So we have W0, W1, W2 until WD, and suppose that we have one output here. So what we are having is that in this neuron, first on this side, we are calculating a dot product between W and X. So W transpose X, which is basically W0X0 plus W1X1 plus etc. plus WDXD. And then on this side, let's say this is called something like Z. On this side, we apply another function on this Z. So basically we are applying a function on W transpose X. And this output is going to be basically, this Y is going to be equal to F of W transpose X for us. Okay, so this is a very basic neuron. that we have. So this F is adding usually non-linearity, and this W transpose X is just a linear combination. Okay, note that we are, this can be our output, right? So note that what we have here is a d-dimensional X. So basically for each data record, if we have our data is an n by d plus 1 augmented matrix, then it's as if we are having one row at a time as the input to our deep network or neural network. So usually what we say is that this is the input. We call this each stack of nodes that we have a layer. So we have an input layer, and also we have, this is an output layer, right? And in the middle, we have this neuron, and you will later see that we call it hidden layers sometimes. So one good thing about neural networks is that they are very flexible. So depending on the choice of F, and depending on the W's and how many layers we put in between, we can represent different functions with neural networks. So that is a very good thing. So for example, we can represent what we have learned so far, like logistic regression or a simple regression with neural networks also. And we are going to see that pretty soon. So usually what we do is that we give specific names to what we are doing in each of the neurons. We said that in each of the neurons, we have some linear combination of the input with the weights, and that is called aggregation. So first we do an aggregation, and in aggregation, what we are doing is that we are calculating a net input, right? Which is basically this linear combination calculation, which is W transpose X, right? And as we saw, our X is the augmented vector, right? So we have X1 to XD as our original d-dimensional data, but we add this X0, which is always equal to 1, as the augmentation. And sometimes what we do is that instead of, similar to regression, instead of having W0, we use B sub K as the baseline for our coefficient for this augmentation for the data, right? So if my neuron is neuron number K, so I can represent it with Z sub K, and each of the weights that are going in the neuron are also have K index in it also. So that's the first thing that we do in a neuron. We do aggregation. We calculate a net input. So if I have Z sub K, I can call this aggregation net sub K, for example. The next thing that we do in a neuron, we said that it is applying a function, usually nonlinear, on the aggregation. So what we do is that we say Z sub K is equal to, so Z sub K is both the name of the neuron and the value of the output, is equal to F of this W transpose X, which we called it net, right? So it's F of net K for us. Now, applying this function, we call this f activation function. Okay, so basically we can say that in an artificial neuron, we have two things that are happening. First, aggregation, and then activation. Okay. Now, what are the choices of these activation functions? We can have different kinds of functions for f. Now, we are going to see some of these activation functions, and we are going to see some of the properties of them. So the easiest one is just a linear activation function. When we have a linear activation function, it kind of works as an identity function. So we can say that f of net k is equal to net k itself. So basically, if I have my input x0 until xt, and then they are all going into the neuron, and I have these w's, and f, basically our output, or f of net k, in this case, is going to be equal to w transpose x. X tailed off or augmented, or w transpose x plus b for non-augmented case, right? So this is the simplest activation function that it's as if you're just doing linear combinations when we are applying this in a neuron. A little bit more different is a step function. Now, in a step function, if the value of the linear combination that we have is more than 0, it is positive, then the value of step function is going to be 1. Otherwise, it's going to be equal to 0. The step function is usually not used that much because when you are going to see that we are going to use an algorithm that is backpropagation that it's like gradient descent that we have learned before, and it has a difficult condition in which there is a disjunction in the function that we have, and it makes the derivative going back in the backpropagation to be difficult. So people don't use the step function that much, but this was one of the first functions that people introduced. Another activation function that is used a lot is rectified linear function, or ReLU. So ReLU is also kind of disjoint at some point, but what it does is that if the value of the linear combination that you are calculating, if net sub k is positive, it works similar to a linear identity function. So if net k is positive, the value of this function is going to be equal to net k. Otherwise, if it's negative or 0, it's going to only be 0. Okay, so in all of these, if we apply this on the W transpose X plus B on the whole thing, for example, the ReLU function is going to look like this. So when it is larger than 0, it's going to be equal to net k. Otherwise, it's going to be equal to 0. But if we take b out of this equation, then it's going to shift this function a little bit. You can see that it's shifted a little bit towards negative minus bk. But that's just a detail, right? So in ReLU, he said that if the value of net is positive, then it's going to be similar to identity function. So for example, because we are going to need to take the derivatives of all of these functions when we are learning the parameters in neural networks, let's look at the derivative of ReLU function. If I want to take the derivative of this function, then at this point, when I have the linear part, the derivative is going to be equal to 1 with respect to net. And at this point, the derivative of it with respect to net is going to be equal to 0, right? Okay, so rectified linear, or ReLU, is one of the popular activation functions. The next activation function that is also familiar to us is the sigmoid function. So we have seen the sigmoid function in logistic regression already, right? So it is equal to 1 over 1 plus e to the negative net. And it's basically a very smooth version of the step function, right? So in step, what we had was something like this. Now in sigmoid, what we have is a smooth version of step, right? So if we want, we can actually get close to the step function by just adding a beta coefficient. So instead of having 1 over 1 to 1 over 1 plus e to the negative net, what we can say is that we can have a multiplier before net, and we can say it's equal to 1 over 1 plus e to the minus b net, right? And if we increase b, as we increase b, then we are going to get closer to step function. Okay. But there is a problem with the sigmoid activation function, and that is that when we look at the derivative of this sigmoid activation function, we have seen this derivative before with respect to net, it's going to look like this. So the derivative of f is going to be f of net multiplied by 1 minus f of net. And the derivative, if f of net is equal to 0 or close to 0, the derivative is going to be close to 0. Also, if f of net is close to 1, it is also going to be close to 0, right? Because 1 minus f of net is going to be 0 almost, and this multiplication is going to be 0. So in many cases, as we get closer to the ends of the sigmoid function, the derivative is going to, with respect to net, is going to get to close to 0. And in gradient descent or gradient ascent, gradient-based optimization, we need the gradient to be some value other than 0 so that we can get the updates, right? You remember that when we did the updates in gradient ascent, we set the new W to be the old W plus some multiplication of the gradient of the objective function with respect to W, right? So that was gradient ascent. If it's gradient descent, so we are looking for finding the minimum of a function, we went, we did the negation so that we can go to lower values. But in any case, if this gradient is close to 0, then my new W is going to be very close to my old W. So I'm not going to see that much of update in the W. So if I get my gradient close to 0, I'm going to get stuck. I'm not going to change W that much. And the problem with sigmoid function is that in most of the cases, the gradient is very close to 0. Only in this part, in the middle part, the gradient is non-zero, right? It's a value that can really affect our updates. So the problem of using sigmoid function usually in deep nets is that as we get closer to the ends, we are going to see less and less updates, and we are going to get stuck. Okay. So that's one of the issues with the sigmoid function. So another function that is also used a lot is hyperbolic tangent function, or tanh. So in tanh, we are also very similar, it is very similar to sigmoid, but the difference is that instead of being between 0 and 1, you remember that the sigmoid value was between 0 and 1, right? Instead of being between 0 and 1, tanh is between -1 and 1. So basically, we can say that if we don't want to have negative values in the output, we can use sigmoid activation function. But if we are okay with having negative values and positive values both, then we can use the tanh activation function. All right, and basically the function itself is equal to e to the net minus e to the negative net divided by the summation of e to the net and e to the negative net. And if we take the derivative of that, it's going to be equal to 1 minus f of net squared. And finally, the last activation function that I'm going to talk about is the softmax activation function. You have seen softmax before also in the logistic regression with multiple classes, so multi-class logistic regression. And it's basically the same softmax function that we had there. The function of, it is going to be defined according to each of the classes. You remember that we defined a function for each of the classes. So the f of net k for class k, given a net that is a vector that has all the net values in it. So this net is a vector including all net 1 to net p, for example, when we have p classes, is going to be equal to e to the net k over the summation of e to the net i's for all of the i's from 1 to p. And then if we take the derivative, it's very similar to the sigmoid. It's f of net j multiplied by 1 minus f of net j. So now that you are familiar with all the popular activation functions, let's go back and see what kind of functions we can represent with neural networks. I said that we can represent the linear regression and logistic regression models using neural networks, right? So how can we do that? Let's see. So linear regression is very simple. In linear regression, what we had was that we said y is equal to w transpose x, right? X, if x is augmented x tilde, or it's equal to w transpose x non-augmented plus b. So this is as if we have a neuron, and then we have our input layer X. So we are going to have X0, X1 until XD. And we have the weight. So this is B, which is basically W0, W1 until WD. And this is going to generate our Y. So here we have W transpose X, right? And our Y is actually equal to W transpose X. So our F is going to be the identity linear activation function, right? So Y is going to be equal to W transpose X plus B, or W transpose X tilde. Now, to talk more in language of neural networks, we have to follow their symbols, right? What usually people do is that for X0, they put it in 2 circles as the augmentation variable that is always equal to 1. And for all other variables, we have just simple circles around them. And also, usually instead of Y, we have O, which stands for output in the last layer. So output layer, input layer, and this is our neuron. Okay, so this is our linear regression, represented as neural networks. How about logistic regression? Well, in logistic regression, it's if we have 2 classes only, it's very similar to linear regression. So in case of binary logistic regression, what we are going to have is, again, the same X0. Oh, this is very ugly. So X0, X1, etc., XD. These are our input layers. We are having the weights BW1 until WD. We have a neuron. Now here we have W transpose X, but you remember that in binary logistic regression, we had our Y was theta of W transpose X, and theta was the sigmoid function, right? So if I choose my F, the activation function, to be sigmoid, then my output is going to be equivalent to the output of binary logistic regression, right? So that's nice. So let's see an example. For example, if we are looking at houses and our data looks like this. So we have a data. Let's talk about regression first, and then we are going to talk about logistic regression. And we have a data. So we have, for example, n houses in our data set, and our X1 is number of rooms in the house, and our X2 is square footage of the house, and Y is the house price, right? What we are going to have as our input layer is going to be X0, which is always 1. Then we are going to have X1, which is our number of rooms, and X2, which is square footage. And then we are going to have B, W1, W2, And then our y hat is going to be equal to O, which is, because F is linear, it's going to be W transpose X, or it's going to be W1 X1 plus W2 X2 plus B, right? Now, because we have n data points, every time what we have in our input layer is going to be x0i, so the ith data point, x1i, x2i, right? And then we are going to get yi as a result. Okay. Or if, so in the input layer, it's as if we are having one neuron per each attribute, but it's the input layer neuron doesn't do anything, basically. Now, what if we have, instead of y being price, what if we have y being price level? So for example, is it high? Is it medium? Is it low? Etc., etc. So instead of having a numeric value for y, if we have a categorical value for y, then our problem is not a linear regression anymore. It is a logistic regression. It's a classification. We can use logistic regression for that. Now, because we have 3 categories here, we cannot use binary logistic regression, right? We are going to have multi-class logistic regression. So if I have a multi-class, how can I show it in neural networks, or how can neural networks show that for us? You remember from multi-class logistic regression that we learned a different set of parameter W's for each class, right? If we had P classes, we learned a vector W1, W2, etc., until WP, one vector for each class, and all of these vectors together actually made a matrix for us. So here we are going to have a similar situation. So our input is the same. I have my x0, x1, x2, xd. So similar to this example, I have x0, which is always 1. x1 can be number of rooms, x2 can be square footage, x3 can be number of bathrooms, etc. But because I'm learning a different set of parameters for each of the classes, I'm going to have one neuron per class. So this is for class 1, this is for class 2, etc. This is for class P. So this for class 1, right? So this is going to give me output 1. This is going to give me output 2, and I'm going to get output P out of the last one. What are these outputs? They are basically this f of net k associated with class k given all of the net values, right? So basically what we are going to have is that we are going to connect all of the input layer neurons to all of the output layer neurons, and for each of them, we are going to learn different parameters. So for example, for class 1, I'm going to have W0 for class 1, W1 for class 1, W2 for class 1, until WD for class 1. For class 2, I'm going to have, oh, sorry. For class 2, I'm going to have all of my input layer connected to class 2 with different weights. So I'm going to have W0 for class 2, W1 for class 2, W2 for class 2, until WD for class 2, right? So these are the set of parameters, the vector of parameters for class 2 for me. For the last class also, so for all classes, I'm going to have that, right? So for the last class, I'm going to also have this. So this is W0 for class P, W1 for class P, W2 for class P, WD for class P, right? So the vector of W's that I'm going to learn for class 1, I'm going to learn vector W1, which is like this, W0, W1, until WD. For class 2, I'm going to learn another vector, W2, which is W0, W1, until WD for class 2. For class P, I'm learning another vector, which is W0, W1, WD for class P. Okay. Now, this is just calculating the nets, right? So what we are doing here I'm calculating net 1, and this is going to give me net 2, and this is going to give me net P, right? So net 1 is W1 transpose X, and net 2 is W2 transpose X, and net P is going to be WP transpose X. The notation is a little bit messy, but you get the idea, right? Now, we have done all of the nets, but we haven't calculated the outputs yet. Why? Because we haven't done the activation yet. What kind of activation function do we have? Our activation function is the softmax function, right? So for our class 1, our output 1 is going to be softmax over net 1, which is net 1 over sum of I equals to 1 to P net I. Right? Sorry, E. I forgot the exponential. So it's E to the net 1 over sum of E to the net I equals to 1 to P. O2 is f of net 2, which is E to the net 2 over sum I equals to 1 to P E to net I, etc., etc. Okay, so this structure, this architecture is going to calculate the logistic regression for us, right? So basically, so far, we have learned that using neural networks, we can calculate the logistic and linear regression. We can represent these two functions. Now, you remember that when we were working with logistic regression and linear regression, our goal was to learn the parameters, learn the W's that would have matched our data the best, right? So our objective, we defined an objective function, and we tried to learn the W's given our data set. Now, here also, we have a similar situation. So we have the neural network architecture, we have our input data, we have our output data, and our goal is to calculate the W's that best match our data given an objective function. All right. Now, let's see an example of using artificial neural networks for regression. So in the book, we have this data set for irises that have different sepal lengths and petal lengths. We have 150 data points. And if we run linear regression on sepal lengths and petal lengths, right? And we want to predict the petal width in this data. So our Y is petal width, and we have X1 as sepal length and X2 as petal length. If we do linear regression on this data set with 150 points and 2 attributes, 2 independent attributes and 1 dependent attribute, which is petal width, then we are going to get to this solution. So this is going to be the W's that we are going to learn from regression. And the error, the squared error that we are going to get for this solution is going to be equal to 6.179. Now, if we use this neural network here for this data to learn the W's and the parameters, we are going to see that we are learning W's that are very close to what we have learned in linear regression. So if we use an linear activation function and the neural network above, these are the parameters that we are going to learn, and our squared error then is going to be equal to 6.18, which is basically meaning that these two solutions are equivalent to each other. Another example is using artificial neural network for multivariate regression. So again, there is this data set of sepal lengths and sepal widths and all of that in our book. And if we want to do some classification of petal lengths, now one is for petal lengths and the other one for petal width, then we are going to, if we do multivariate linear regression that you haven't seen in this course, but it is in the book if you would like to check that, we are going to get to these set of parameters. And these are going to be our output data. And then using that, we are going to get a squared error of 84.9. But if we actually do the multivariate regression instead of neural network, we are going to get a very similar squared error, 84.16. So these are just demonstrations that these two neural networks, the structure that we have seen, and the linear regression or multiple regression, they're all going to be very close to each other. And this is a visualization for multi-class logistic regression. And you can see that for each of the classes, we are having a softmax. So this is for class 1 here, this one is for class 2, and this one is for class 3. And our data points are classified based on these softmax functions, and these ones are just the outliers. Okay. Or not outliers, but the errors that we are getting. Okay, so this is another example very similar to what we have seen before, basically illustrating that they are logistic and linear regression can be represented by linear neural networks. Okay, so again, we said that our goal now is to be able to learn these parameter W's. If you don't learn W's, we cannot calculate anything, right? So we want to learn W's according to our data. So we need to have an objective function or a loss function to be able to learn the W's based on that function, right? So we want to find the W's that when we apply the objective function, then we can optimize that objective function or the loss function with respect to W. So you remember, for example, in linear regression, we defined squared error, squared loss, that was basically the squared difference between the predicted values and the actual values, and that was our objective function. And we wanted to find the W's that, based on our data, minimize this loss or error, right? We want to find the W that we have the least amount of error possible. Or in logistic regression, you remember that we had this log likelihood. So logarithm of likelihood of our data according to the parameters. And because it's likelihood, our goal was to maximize the likelihood. Our goal was to basically see the likelihood of the data that we have seen to be as big as possible. And you remember that in logistic regression, this maximum likelihood was basically equivalent to minimizing the cross entropy error, right? So here in neural networks, we are also having a similar situation. We have to define some kind of loss function or objective function so that we can learn the weights W's. So one of the loss functions that we can have is also squared error, similar to linear regression. So what we are doing here is that we can compare the output of our network, or O, with the value of our response variable in the actual data that we have. So basically we are comparing our O, the value outputs for each of our records, data records, with the Y for the same data record. And that is going to give us the squared error or a kind of loss that we can learn. Right? And of course, we are summing over all the instances. So epsilon, or the error, is going to be the error on each of our inputs. So for example, if we have multiple inputs and multiple outputs, then we can sum over all the outputs for each of our data points, right? And that is going to be the error on our input X. Then to optimize this error and find the best W's, what we can do is that we can use the gradient descent algorithm. So similar to gradient ascent, that we move towards the direction of gradient to go to larger values of the objective function. Here, we want to minimize the objective function. So we go in the direction of negative gradient, or the opposite direction of the gradient, to get to lower values of the objective function. And in stochastic gradient descent, we are going to look at each data point one by one. So we are going to have a partial derivative of this squared error with respect to each of the outputs. Okay. So this is for one of the error functions that we can have. But if our response, if our output is categorical, instead we can use cross entropy error, right? So cross entropy error is going to be basically similar to like the other side of logarithm of likelihood, and we have seen that before also, and it is equal to multiplication of our real response variable yi with the logarithm of our output variable, or the predicted output oi, right? And if we have k or p different output neurons, we are going to sum over this value for all of the neurons in the output layer, right? And of course, negative of it. So this is the cross entropy error for when we have a classification task, when our output variable is categorical, it's not numeric. All right.